This is the 26th lecture of EP1. We are slowly moving away from mechanics and slowly moving into the realm of thermodynamics. Thermodynamics is the part of physics that studies the laws that govern heat and thermal phenomena. Unfortunately, we will have very little time for thermodynamics. We will go over the absolute basics, and I'm hoping that later Department of Engineering will offer you classes in thermodynamics where you will get a chance to learn base things in much greater detail. Because thermodynamics is one of the most beautiful subdisciplines of physics, it's very rich in useful and beautiful results. This week we will be talking about engines. The basic idea behind engine is the following. We know that everything is made of molecules and atoms. We know that they move around. And we know that there is lots of energy in the thermal motion of molecules and atoms, because there are lots of them and they move pretty fast. Unfortunately, it's not easy to turn this thermal energy into useful energy. It's easy to go the other way. If you have something that's moving, it's pretty easy by engaging friction to turn energy of a ball into thermal energy of molecules. It's not that easy to go back and harvest energy of molecules and make it move an object. Engines are devices that do this, that under some circumstances can take thermal energy and convert it into mechanical energy of motion. So how does this happen? Usually when you have an engine, you have two reservoirs. One of them is hot, so this could be a hot reservoir. And then we have a reservoir that's cold. Molecules are moving much, much slower here. And we know that if we make these two interact somehow, then energy, heat, will flow from the hot object to the cold object. And as energy flows from the hot object to the cold object, it is possible sometimes to redirect some of this energy into useful work. And devices that do this are called engines. So with the internal combustion engine that we have in our cars, we create this hot and cold reservoirs by burning fuel inside cylinders. When the fuel burns, the inside of a cylinder gets very hot, and the exterior is obviously cold. The hot gas expands and does some useful work for us. So there is this engine is a complicated version of this cartoon that I drew on top of my whiteboard. Unfortunately, we don't have nearly enough time to cover the practical aspects of how engines work in any useful detail. So what we will do is we will just concentrate on the very basic and very fundamental laws that govern engines. And these will be the laws that every engine, no matter how it's made and how it works, must obey. I'm now moving to slide number 3, where I have this schematic picture of an engine. I have something at high temperature and something else at low temperature. Obviously, the heat will flow. The hot reservoir will lose some amount of energy. Let me call it QH. And let's say I have an engine and I can redirect some fraction of this energy as useful work. And then there will be some leftover thermal energy that will be dumped into the cold reservoir. So this is QL. Now, this is a very schematic view of an engine. We don't really know how this works and how the gears turn. So you may be wondering if there is anything at all that you can say about an engine if you don't even know how it works. But turns out that we can, there are a few things that you can know about the engine, even if you don't know anything about its internals. So let's start with the very basic things. First of all, we know that energy is conserved. You cannot create energy and you cannot make energy disappear. Energy is conserved, and in first few weeks when we were saying that energy is lost, what we meant was really that the energy, mechanical energy, goes into thermal energy. And since energy is conserved, these three quantities cannot be independent. They are linked. QH must be equal to W plus QL. So this is the amount of heat, original heat, and this is part of it is spent on work, part of it is spent on heating up the cold reservoir. But since energy is conserved, this equation must be satisfied. Since we're in most cases interested in work, we will sometimes rewrite this equation like so. The work, useful work, is the amount of thermal energy that we take from a hot reservoir minus the amount of thermal energy that we dump into a cold reservoir. Now, the more work we do, the more efficient the engine is. If somehow it was possible to take all this work, all this thermal energy, and convert all of it to work so that there was no QL, then this would be a perfect engine that would be using all of the thermal energy available to it. So this would be a perfect engine. To describe how close real engines are to this perfect picture, we use efficiency, and efficiency, usually denoted by Greek letter epsilon, is work divided by the amount of heat. So this is basically the total amount of energy, and this is what fraction of it we managed to make into useful work. If for the perfect engine, W would be equal to QH, and epsilon would be equal to 1. So 1 means 100% efficient engine. Real engines, of course, have lower efficiency, and the efficiency of real engines is somewhere between 0 and 1. Now, if I have an engine, I know that its efficiency has to be, cannot be more than 1. Is there anything else that I can say about this engine without really knowing how it works? So it's very surprising, but turns out there is something that I can say about the engine without knowing anything about its internals. And so this is a work performed by a bunch of 19th century French physicists. The basic result, without deriving it, I will quote it here, is that if you have an engine that works between two temperatures, some high temperature TH and some low temperature TL, then the maximum efficiency that this engine could have is 1 minus T cold divided by T hot. So this is the maximum efficiency. Now, this is a very surprising result. It tells you that if you have your hot reservoir at a certain temperature and your cold reservoir at a certain temperature, those temperatures basically bound you from above. They set an upper efficiency that you could never exceed, no matter what kind of improvements you make. So the thing that binds from above the efficiency of your engine is the temperature at which it operates. let's look at this equation more closely. This is really a simple equation from a mathematical point of view. So a few things. If T cold is equal to T hot, then my efficiency is equal to 0 because it's 1 minus 1. So this tells me that unless I have some temperature gradient, I cannot get any work out of my engine. If everything was at the same temperature, there would be no way for my engine to extract the thermal energy and to convert it to work. Now let's think about how I make my efficiency high. If I want to make my efficiency high, my cold temperature has to go down and my hot temperature has to go up. So more the gap, the more efficient my engine is. The next question you may be asking is, under what circumstances can I achieve epsilon equal to 1? So this perfect engine. If you look at this formula and if you trust this formula, then unfortunately from this formula, it follows that the only way to achieve maximum efficiency is if your cold temperature is 0. So you must have some sort of engine where fuel burns and then the outside is cooled to 0 degrees. Now, there is one thing that I forgot to mention, and this is a very important thing. When you're using these formulas, so this formula, you have to use Kelvins, so Kelvin scale. This doesn't work with Fahrenheit, doesn't work with centigrade. In most cases in physics, it doesn't really matter what units you use as long as you're consistent. But there are some places in thermodynamics where you really must use Kelvins, otherwise the equation doesn't work. So for this equation, you have to use Kelvins. And then it follows that to have a perfect engine, you have to cool it down. You have to cool its surroundings to 0 degrees Kelvin. That's absolute 0. It's not achievable. So unfortunately, even though the conservation of energy allows it, the perfect engine where all of the heat is converted to work is unfortunately in practice impossible. And all of this follows from this one simple equation for the efficiency of an engine. Now this is, again, to remind you, this is the maximum efficiency for an engine that works between this and that temperature. And this is the efficiency you will get if your engine is otherwise perfect. In real life, engines are of course not perfect otherwise. So real engines, don't really reach this maximum efficiency. The real efficiency is lower than the maximum efficiency. This perfect engine that would extract the maximum possible work from an engine is called Carnot engine or Carnot cycle. I believe he's silent because Carnot was a French engineer and physicist, so Carnot's engine. So we will very often refer to Carnot's engine. When you hear Carnot's engine, this means the most perfect engine that could exist between these two temperatures, but real engines are of course less efficient. So as I said, we don't really have time to go over specific engine designs, which is a pity because this is very interesting. I tried to put some basic links into my slide number 4. Watch them if you have time. There is Otto cycle, Atkinson cycle, and diesel cycles. And then if you're interested, you look up more in-depth explanations on YouTube. Carnot's engine is, unfortunately, even though it's the most efficient, isn't always very practical. So we have to make some trade-offs. one of the trade-offs that engine makers often have to make is they have to balance efficiency versus maximum power. So it's not always the case that the most efficient engine is also the engine that provides most power. And sometimes you go after power instead of efficiency. So in real life, these kind of trade-offs have to be made. On slide number 5, I have one slide about refrigerators. So refrigerators are basically, for our purposes, they are engines in reverse. We already talked about how if you have a hot reservoir and if you have a cold reservoir, energy will flow from hot to cold. And by the way, it's not that trivial why energy flows from hot to cold. And we will talk about this a little bit in our last lecture, lecture 27. But for now, let's take it granted that energy always flows from hot to cold. And the engines were devices that would steal some of this energy. So this is an engine. Refrigerators or heat pumps are kind of engines in reverse. You have a hot reservoir, you have a cold reservoir. And what engine does is, what refrigerator does is refrigerator moves some energy from cold to hot. Now, this is of course unnatural. This will never happen on its own. So to make this happen, you have to do some work. You have to put some energy into this process. So this is an engine. This is a refrigerator. This is high temperature. This is low temperature. So this is the amount of work that I do. And with this work, what I do is I remove some heat, some thermal energy from low temperature, and I move some amount of energy, I dump some amount of energy into high temperature. Again, we're not going to talk about specifics of how this exactly is done. We will just refer to the schematic picture. So how is not important now. The question is, we will take it for granted that this can be done, and we will look at the ways of describing this process. Again, if you think about this from the energy conservation point of view, it will become clear that QH must be equal to QL plus W. Because you start with some energy QL, you do some work, which is extra energy. So QH is the amount of heat that you dump. This is conservation of energy. This has to always be true. And if you look at this equation, you will see that QH is always larger than QL. So when you take some heat from your fridge, you always have to dump more heat into the environment. So refrigerators, even though they make small compartment cold, on average, they make the universe hotter. Now, how do we describe efficiency of refrigerators? For the engines, we had efficiency as work divided by QH. So this is kind of useful energy. This is total energy. And for refrigerators, it makes sense to define coefficient of performance, K, to be QL divided by W. And this is because for refrigerators, we actually want to perform the least amount of work and to move the most amount of heat. So amount of heat removed divided by the work, if this number is high, that's good. If this number is low, then it's not as good. And now you may be asking yourself, as for the engines, we had we knew that the efficiency couldn't possibly be more than 1. This was impossible because of the conservation of energy. But then turns out there is an even stricter bound that tells you that efficiency cannot be more than 1 minus TL over TH. Is there a similar formula that restricts how well a refrigerator can work, is the question. And the answer to this question is that yes, there is a pretty similar looking formula. And the formula for the maximum possible coefficient of performance of a fridge is that it cannot be more than temperature low divided by temperature high minus temperature low. So what do we do to get high coefficient of performance? We either increase TL or we decrease the difference between TH and TL. So basically what this is telling you is that if TH minus TL is a small number, then our performance will be good, which kind of makes sense because if you have to cool something down, it's more difficult to cool things down if everything outside is really, really hot. If everything outside is already pretty close to the low temperature that you are aiming at, then your refrigerator will perform well in a sense that it will be easier for it to remove heat from a cold place and dump it into a hot place. So this is refrigerators and that's engines. Just to summarize, in terms of formulas, this week is kind of simple. The only two formulas that we have really are the formulas for the efficiency of the engine and performance of the refrigerator. Efficiency of the engine is 1 minus T. Let me write this. Efficiency of the engine is, yeah, let me write it this way. Work over QH, where QH is the amount of thermal energy that moved. And for the refrigerator, coefficient of performance is it's QL divided by W. In both cases, high coefficients are good and low coefficients are not so good. And for the maximum possible efficiency, for the engine, we have 1 minus T cold over T hot. For the refrigerator, we have T cold divided by T hot minus T cold. So these are the only formulas that I believe you need for your homework. And the important thing not to forget is that in these formulas, it's very important that temperature is in kelvins. So I will pause here. This is slide number 5. And in the second half, I will go through some questions and problems from your textbook, and I will try to solve them on the board.